record. Okay, so this is partial fractions. We use this method specifically for handling integral expressions which are rational in form. So when we speak of rational, we have a numerator and we have a denominator. But specifically, we use this for rational expressions in which the degree of the numerator is less than the degree of the denominator. Because if the degree of the numerator is equal to or even greater than that of the denominator, you are dictated by the previous topics discussed that you need to perform long division. You perform long division, and then after you have done that, then that's the time that you will process your answers per term. You will evaluate the integral of each of your terms in your answer. That is when the degree of the numerator is equal to or greater than the degree of the denominator in your fractional form of your integral or in your rational integral expression. So let me go now to main business this afternoon, and that's on the topic of partial fractions. Okay, let's say for example, you're given the integral of 5x minus 3 divided by x squared minus 2x minus 3. So in this integral, if you will inspect, that's the first thing that you will do, the degree of the numerator is less than the degree of the denominator. So meaning that tells you more or less that you will perform method of partial fractions. However, in the method of partial fractions, you are required that your denominator has to be in the least factored form, meaning if this one is in the quadratic form, try to check whether this can be factored. Okay, so we will write this particular expression here. So this would be a lot easier if we can rewrite it as two separate terms. What does this mean? Check whether this one can be factored. So now, from your algebra, you have learned that x squared minus 2x minus 3 is just equivalent to x minus 3, quantity x minus 3 times quantity x plus 1. So you have an x squared for this one. You have a negative 3 for the product of this one. The sum of the product of these two terms, negative 3x and x, is negative 2x. So if you're going now to process this original integral, it has to be in this form in which the denominator is already factored. Okay? Now, once your denominator is already factored, you are going to write this original rational integral form that is provided into what we call its equivalent partial fractions. We call this the equivalent partial fractions of these two. However, if you notice, there are constants in the numerator here that you need to first determine the value of before you determine the integral of these separately. So how do you accomplish finding the values of these two undetermined, we call this undetermined coefficients or undetermined constants? What you're going to do, you are to multiply your original given expression by the the factored form of your denominator. That way you will see what you need to multiply with A and what you need to multiply with B. But before we're going to do that, this first example is actually a case of what we call a non-repeating linear factor, or shall we say, this is a case of unique linear factors. We call these factors. They are linear because the exponents of the x are all 1, and they are unique because this one is different than this. So we call this non-repeating linear factors or unique linear factors. So you may already know a shortcut for this problem, and we will go to that in a few minutes. But for now, we'll not, of course, do the shortcut unless you understand how the real thing is to be done. So multiply by the common denominator. So the common denominator is x minus 3, quantity x minus 3, and x plus 1. If you do that, your A should be multiplied by x plus 1, and your B should be multiplied by x minus 3. Why is that? It's because your A has the factor as x minus 3 only. So as what you have learned in your algebra, whatever factor is not written in the fraction of the two fractions in which you have this least common denominator, that factor should be multiplied to its numerator. So this one is only x minus 3. You lack the x plus 1. So A should be multiplied to quantity x plus 1. You use the same principle in the case of the second partial fraction. So it has only x plus 1. So B has to be multiplied by x minus 3. Now you can do expansion, although I don't suggest that you do expansion. I will simply call this method, you equate coefficients of terms that are similar. Okay, so if you, however, expand it, it would be in this form. Okay, if you expand the right side, that is. Now set like terms equal to each other, or you equate the coefficients of terms containing the x and of the constant. So if we do equate coefficients of the x, you will have here a 5. You have here x also, so an a, and you will have a b. So all x can be cancelled, leaving you, I'll go to this, 5 being equal to a plus b. Now from this same equation, if you equate the constants, so left side has negative 3, right side has a, and you have here negative 3b. So a dot here implies that you are actually looking at the product of 3 and b. So you have negative 3 is equal to a minus 3b. Okay, now we have two unknowns, right? A and B in the first equation, another A and B in the second equation. So this is just a case of algebra. Two equations with two unknowns will help you solve for A and B. So you deal with these two equations to solve these two equations with two unknowns. And you substitute for your, this one, your A here. If you add the two equations, this one being multiplied by negative 1, so that this A becomes negative. So this becomes positive, and this one becomes negative. You add, you eliminate the A, that gives you B, and that would be giving you a B of 2. If B is equal to 2, actually you can choose from either of the two equations to solve for A. But this is just one of the many methods you can use. So in this case, A is equal to 3. So this is just but one of the many methods you can use, that way you can find A and B. This is the method of elimination. You can also use the method of substitution. I will not discuss it here because this is not an algebra class, okay? But nonetheless, this is the value of A and B. Now, what will happen if you know the value of A and B now? You can integrate these two partial fraction equivalent of the original by integrating them separately. So I will annotate in this slide, that way you can follow too. I'll just use the color blue. So what will happen now is that from in here, the original integral, this would be equal to the integral of your A is equal to 3, and that would be dx over x minus 3. I'm getting it from here. And your B is 2, so you have a 2 integral of dx over x plus 1. Now we're done with this topic. So the denominator is x minus 3. In the first integral, the second one is x plus 1. These actually expressions will yield a natural logarithmic expression. Why would that be the case? Because if this is your u, this is your u, this is your du, and this is your du. U is x minus 3, the du is dx. U is x plus 1, the du is dx still. Then this is an ln. So if we will continue, your answer for this one is this one, the 3 ln of x minus 3 for this. And this one is 2 ln of x plus 1 plus c. Now this one is already, again, This is the answer already. I'm referring to this one. This is the answer already to the original integral. Your original integral has this as the answer. This technique that we just performed is the method of partial fractions. These are the partial fractions equivalent of the of the original integral. Okay, and in this first example, you're dealing with linear factors which are unique, meaning they're different from each other. So if you have a linear factor, what you have on the numerator, so I will again annotate here so you will recall what you will have on the numerator. Why can't I write? Are constants A and B. So these two letters are just arbitrarily used here. So you may use any letter that you like. Okay? Now we go to the next example, but before we go to that, of course, let's clear all these markings. So this is our answer for the first part. Okay, we go to the next. Now, if this same integral is processed using the shortcut, so before I teach the shortcut, I always teach the long process. That way the student will be able to appreciate, because sometimes the shortcut method of whatever that may be, on whatever topic that may be, or in whatever course that may be, does not really fully explain the concept behind or the principle behind that was used. So the shortcut method is the heavy side, but before you perform that, it's the same thing. The same procedure that you will do, you multiply the original expression by the common denominator. This is the common denominator resulting to this one. Now, what is this Heaviside method? Named after the English engineer Oliver Heaviside. You think of a constant that you will assign to the x in this expression, specifically on the right side, that will eliminate one of these two constants. So if I think of 3, if I would think of 3 here, this b will be eliminated because my b will be multiplied to 0. That will help me solve right away for a. If I think of negative 1, a here will be multiplied to 0, then this particular term will be 0. That would then lead me to determining the b. That's what we do in Heaviside. The downside of the Heaviside, or shall I say not the downside, but the limitation is that it's only working for linear factors. So meaning if you are dealing with quadratic factors, you will be still using the long method. That is why it's important that you still know the long method. Okay, so if we would do Heaviside, so you can have x equal to negative 1, this will be 0. You assign negative 1 here, so this would be negative 4b. If you have negative 1 here, that would be negative 8, giving you a b that is 2. So the same as the previous process. If you let x equal to 3, this would be the one that would be 0. This would be 4a, and this would be 15 minus 3, that would be 12. 12 divided by 4, that will be a 3. So the same answer as the previous. So with these 2 for B and for 3 for A, and go back to the previous one so you will see. You will then process, so it's 2B and here 2 for B and 3 for A. You will still process the same integral afterwards. So it's shortcut for linear factors only. This shortcut will not be able to make a shortcut to the answer if your factors are, as I've said, non-linear or quadratic. Okay, so this is your second way of determining the solution to this rational integral. Now let's proceed. What about this one? Okay, your denominator is linear, x plus 2, but it's raised to an exponent, so it's already 2. So this is a case of what we call a repeated linear factor, or what we call we have repeated roots. this one repeated itself twice. So how would you write the equivalent partial fractions of this particular integral? Now, if you will write the equivalent partial fractions of this integral, this would be something like this. So it's the same actually as what we have done in the previous example. So you have here a over x plus 2 plus b. Since it's still x plus 2, you will place here x plus 2 as well. But you will square it. Should this be a 3, you should have another fraction here, c over x, or quantity x plus 2 raised to 3. Okay? Now, after this, I'd like to close this one. After you have written this into its equivalent partial fractions, you multiply it by the common denominator, which is this one, telling you that the a should still be multiplied to another quantity x plus 2, and b should be simply multiplied by 1. This one becomes 6x plus 7. You can use Heaviside because in this case, if you use Heaviside, you can solve right away b, or you can equate coefficients, the long method, in which method, either which you will find the value of a and b. So that's it. In here, I have equated coefficients. So your a is equal to 6. The terms that has the x, then your 7 should be equated to 2a plus b, because 2a and b are constants on the right side, just like 7. So your a is 6. You substitute it here. This would be a 12 subtracted from 7. So that would be a negative 5. Okay, so your a is 5 and your b is negative 5. And you go back to your partial fractions and integrate. Okay, these are your two coefficients. Now, how did this came about? Okay, how this particular integral came about? So let's see. You will have, we'll annotate. This one now will be the integral. So your a is 6. So 6 dx over x plus 2. And this one, your b is negative 5, integral of dx over x plus 2 squared. Now, these are not your integrals yet. These are not your integrals yet, but rather these are just your equivalent partial fractions, not yet the process integral. So if you're going to process, it would be 6 ln of x plus 2. And if you use power rule here, this would be a 5 over 3. Oh, sorry. This would be negative 2, so that would be negative 1. Let me erase. So it would be negative 1. This is x raised to negative 2 plus 1. That would be negative 1. Negative 5 over negative 1. That would be positive 5. So that would be plus 5 over x plus 2, because your corresponding answer here when you use power rule is quantity x plus 2 raised to negative 1 plus c. So this is the integral of this original expression. The one that is circled here is just the equivalent partial fractions of the original. Okay, so I will, let me go back first. Do you have any questions so far in here? So this is just but your partial fraction. The answer to the integral is this one. Do you have any question? Okay, none. So let's proceed. So let me just erase the markings. Okay, what about this? The degree of the numerator is 3. The degree of the denominator is 2. So what did we say about this? When the degree of the numerator is equal or greater than the degree of the denominator, you need to perform long division. So you perform first long division. So if you perform long division, the answer will be a 2x for the first, then you will have this. Then you will have 5x minus 3. So this is your remainder. I'm referring to 5x minus 3 divided by x squared minus 2x minus 1. This one, the remainder here is actually the sample problem number 1. Okay, this is our sample problem number 1. So this tells you that you will integrate this and you will integrate this. And since we have the answer to this already, then this is the remaining term to be integrated. So let's move forward. So you have that. That's our number 1. And we have this, the equivalent partial fractions. Then we just, this is your example 1 problem. So if you will integrate, I'll write here the answer. If you will integrate, so this one will be integrated, this will be integrated, and this will be integrated, dx, dx, dx. So your first term will have an answer. So if this is a processed integral actually, so I'll place the dx later. I cannot write it now in here. So your answer will be x squared plus 3 ln of x minus 3 plus 2 ln of x plus 1 plus c. So this is your answer. Based on these answers that you got, one whole number and two rational expressions. Okay, so perform always division whenever there's a need for you to do so. Now we will erase the markings. Now we proceed. So we have here another example. You have now a combination of something new and something not so new. Okay. This is an irreducible quadratic factor, meaning you cannot factor this already. Okay, as is, it's x squared plus 2. But it's quadratic, but it cannot be factored anymore. This one is a repeated root. Now, how will you write down the equivalent partial fractions of this original rational integral? Okay, this is how you do it. For the quadratic factor class, notice that you have here x squared plus 1. So that's your quadratic factor, irreducible, non-factorable. And notice what you have in the numerator. If in the previous two cases, you only have constants, this time for a quadratic factor, you have a linear numerator, a constant, and a constant multiplied by x. Okay? This is always the case when you have an irreducible quadratic factor. Your numerator is always ax plus b or cx plus d or ex plus f, depending on what particular factor you are trying to represent it with. You always have two terms in the numerator. One has an x, the other one is a constant. Now, this x minus 1 quantity squared is accounted for by these two partial fractions. Notice, this is a repeated linear factor. So this one will have only 1 as its constant or numerator, or rather its exponent, the power, and this one has already 2. Okay? Don't repeat wherein you write here c over x minus 1 plus d over x minus 1 still. Your exponent has to increase. If this is 3, you should have another one here. So you should have an e all over x or quantity x minus 1 quantity cube. Notice always remember that the sign, the mathematical operation separating your partial fractions are always positive. So if the C, the D, or any of these coefficients are later on negative, that's the time that you will change the sign of your partial fraction. But as is, it's always represented as positive or plus. Okay, so if we will continue, this is what I'm saying. It's linear. Your numerator is first degree. If we will continue, this will be the resulting expression. Multiply the entire equation by the common denominator. So naturally, the left side would be negative 2x plus 4. This one does not have the quantity x minus 1 squared. So you see it here. This one does not have x squared plus 1 and another x minus 1 because this is just raised to 1, whereas this one is 2. So you have an x squared plus 1 and another x minus 1. For this one, you only need the quantity x squared plus 1. You can do the expansion or you can do the heavy side. But I suggest that you don't use the heavy side because you're dealing here with a quadratic factor. So meaning later on you will still have to equate coefficients. So this is the expanded form. Sorry, that's already the summary. This is the expanded form. So I'd like to copy this and perform the actual process of finding the partial fraction in this case, okay? So let me just get the final equation so I can present it in the solution on the other piece of paper. So I will go to a whiteboard here and explain how you go about determining your answer in this case. So this is how you do it. Your left side is negative 2x plus 4. So I will copy it here again. And you have here negative 2ax cubed minus ax plus bx squared minus 2bx minus b, it's plus b rather, plus cx cubed minus cx squared plus cx minus c plus dx squared and the constant d. Quite a long equation you have here. Okay, so we will equate coefficients. We start with terms that has the x cubed. Now, in the left side, you don't have an x cubed, so this is a 0. No term which has an x cubed. In here, you have minus 2a. Let me underline it so you will see. This is for the x cubed. X cubed and this. So you have negative 2a plus c. This is our first equation. We can solve anything here. Then we'll have x squared. We don't have still x squared on the left, so it's still a 0. On the right, we'll look for x squared. So x squared is this, and this. Terms that has the x squared. So what do? We equate. So you have a b minus c in here, and that one a d. So this is equation 2. Still no sign of hope that we can solve for anything. So let's equate x. Now in here you already have negative 2x. So let's see. So you have this as for the x. Where's the other x? This one. So this is x. This is also x. This is also x. So we will equate x's or terms which has the x's. So I have minus 2. I will not copy anymore the x. Anyway, they all have the x. Is equal to minus a coming here. Here, minus 2b. Where is the other x? This one. Plus c. Now you have this as equation 3. The last would be your constants. So your left side, so for the constants, we have the 4, constant B, and we have the C, and we have the D. Okay? So hopefully I have everything. Okay. Then we will equate constants. So you have a 4 on the left, and you have here B, and you have here minus C, and you have here a D. Equation 4. This is equation 4. Okay? Now we have to make use of your algebra. That way we'll be able to find the unknowns that we're trying to find here. So remember, we're going to find A, B, C, D. Now, if you notice, I like to use a different color here. I'll erase my markings now. Oh, sorry. Why did I erase everything? Is anybody able to copy the equations that I have written?
Ara man miss sa recording, miss.
But I cannot continue without that. So can you please dictate who was able to copy the equations that I have set up? The 4
It tried
equations.
Miss Control Z, Miss.
Control,
Z.
Control Z. Thank you, Iha. You're my angel. Thank
Welcome,
you.
Miss.
Control Z. I was only intending to erase this one. I erased everything. Okay, then I will deal with this 2 and 4. Equation 2 and 4. So you have this one. Why do you have to deal with that, Miss? Because it seems like they have all 3 unknowns there. B, C, D. Similar. So what do you think will be the appropriate letter to eliminate in equation 2 and 4? So from 2 and 4. Any suggestion on what letter will I eliminate? In 2 and 4, remember that I can have A and B here. So I should, A and C here. So I should have B remaining in here. So I will eliminate the C and the D. Okay? Now, we'll see. How do I eliminate C and D in equations 2 and 4? If I will subtract. Look. 0 is equal to B minus C plus D. And I have a 4 being equal to B minus C plus D. If I will subtract, this will be a negative. Wait, everything is gone? Is there something wrong? Wait. 4, and I have constants, a B, a minus C, and a D. In x squared, I have here 0. X squared is a B. And then x squared minus C and D, the same thing. Okay, let me go back to my slide class. Let me check. If I have copied everything correctly, plus. Ax cubed minus 2ax squared plus ax plus bx squared minus 2bx plus b plus cx cubed minus cx squared plus cx minus c plus dx squared plus d. You have x cubed minus x squared plus x minus 1. And you have x squared d. Did I copy everything correctly? I'll go back to our solution. If everything will be eliminated, then how can we solve for, it seems like these two,
I-subtract guro miss para ang C bla miss mabilin.
if you subtract, since they have the same signs, everything will be zeroed.
Ma-negative 2C man siguro miss.
Naaman, kay negative C ka. Zero siya. Dahil lang plus ha. AX cubed. There's a mistake. I saw my mistake now. This should only be AX cubed, not negative 2. Let me erase this one. AX cubed minus 2AX squared plus AX. Okay, so this is where my error is. The first two terms, I copied it wrongly. Okay, so see, you make a mistake in just one term, you will have a lot of things to go back to. So this is AX cubed minus 2AX squared. Then I have minus AX. Oh, this is plus AX plus BX squared minus 2BX plus B plus CX cubed minus CX squared plus CX minus C plus DX squared plus D. Okay, we're good. Now, so in the X cubed, this should be erased. This should be X cubed, this should be only A and C, correct. X squared should be 0, X squared is negative 2A. So I have here so this should be nasalot lang tadi klaso because we have negative 2A here. 2A. Then what is the other one? Plus B. And then minus C plus D. Okay. For X, we have minus 2. We have, this is positive A. That's positive A. And then minus 2B plus C. Okay. For constants, we have 4. And we have here a B, a minus C, and a D. Okay, so I know where my mistake is. So it seems like this one has a minus 2B. I'll place it here. 2A rather. Do you follow? This one has a minus 2A plus B minus C plus D for terms that have the coefficient of X squared. So even if I subtract here, there's still a thing that will remain. So this is minus 4 being equal to, all of this will be gone, and you have minus 2A. So A is equal to 2. If we know A is equal to 2, we can substitute it here. I'll place it here so I can have everything in this sheet. Hopefully, my C will be negative 2. You substitute here, so that would be your C. Now, if A and C are known, I can substitute it here in equation 3. So I have from 3, so negative 2 is equal to my A being 2 minus 2B plus the C. The C, which is negative 2. Okay, correct me if I'm wrong, but if you see that I'm doing something, miss something. So minus 2 is equal to A, which is 2 minus 2B, C is minus 2, correct? So this one, 2B is equal to 2, so B is equal to 1. Yay! So we have known the first three. So we have the C, we have the A, and we have the B. So the remaining is the D. So we can solve the D in the equation that has the least number of terms. So you have equation 4. So from 4, you have 4 being equal to 1 minus, so minus C, minus 2, so that would be plus 2, and your D is D. You're trying to find the D. So D is equal to 1. Yay. So you know now all 4. You know now all 4 coefficients or constants. So A, 2, B, 1, C, negative 2, and D is equal to 1. So let's go to a new sheet. And by the way, we will now write our partial fraction. Okay, so your partial fraction is A being 2. Let me go back. It's AX plus B. If you recall, I will go back to the slide later. So it's 2X plus B, which is 1. So it's 2X plus B all over X squared plus 1. This is dx. By the way, why did I write B? This should not be B. My B here is 1. So my B is 1. This is 1. Now, your repeated linear factor will be for the C and the D. So your repeated linear factor is C, negative 2. So this one, negative 2 integral of dx over x. I forgot what's the denominator, we'll see. And the D is 1. So the D is 1. So you have plus integral of dx over x, but this one is squared. Okay? Now, I'll go back to the slide to see what are the fractions that I have here. I can recall this one as x squared plus 1, but the other two I cannot. So we'll check. So x squared plus 1 has ax plus b, a linear factor in itself, a first degree numerator, and this one is x minus 1 and x minus 1 quantity squared. So we go back to our solution. So this must be x minus 1, x minus 1. This is the coefficient that we saw for C. D is 1, so it's understood to be 1, and this is your A and B. Then you can integrate. So if this is, I'll assign this one, I'll assign a new color here. Why? Doesn't want me to change color. If you set this as the U, the du of that would be 2x, right? Right? X squared plus 1, if this is your u, your du is just dx. So you can actually split this too. This integral can be split in two. You have a 2x dx over x squared plus 1, and another one for this, plus the integral of dx over x squared plus 1, and this one you copy, minus 2 integral of dx over x minus 1, that one integral of dx over x minus 1 squared. This one will yield, if your du is in the numerator and your u is in the denominator, that will yield an ln. So this is an ln of x squared plus 1. This one will yield what? We're done with this. Arctan. Arctan. This is your u squared. This is your 1. So this is plus arctan of u, and that is arctan of x. U over a, but it's only 1. So arctan of x. Actually, you have here 1 over a, but this is just 1. This one is another ln. This is your u. Your du is dx. So 2 ln of x minus 1. This one will be power rule. If this is your u, your du is complete in here. So you just use power rule for this one. So that would be negative 1 over x minus 1. Why? Because this one is negative 2 plus 1. That would be raised to negative 1 over negative 1. So that is why I place this as negative. Plus C. So this is the answer to our integral. The original integral that was shown in the slide. Ln of x squared plus 1 plus arctan of x minus 2 ln of x minus 1 minus 1 over x minus 1 plus c. You can actually simplify these two terms, which has the ln, using the properties of ln you've learned in your EMA 101. When you have minus, it's understood to be what? ln's, in which the argument is being divided. So these two can be placed in here, and the minus sign tells you that this one should be written in the denominator. So class, actually, the final answer could be written in this form. Arctan of x, although this one is correct already, I'm just simplifying it, plus the ln of, this is your x squared plus 1. This 2 becomes the exponent of this, and this entire thing will be in the denominator. So x minus 1 quantity squared, because this one is negative. If it's negative, the argument, this argument of your ln will be written as in the form of a quotient of 2. This one in the numerator, since it's positive, this one in the denominator. The 2, the constants that are written before your ln, are actually exponent of the argument of your ln. Hopefully that was fully covered in your EMA 101. So you have x minus 1 plus c. So this is the simplified form of our integral. The process of method of partial fraction class is really tedious and sometimes long, depending on the degree of the denominator of your given rational integral. But if it's just second degree or third degree, it's manageable. In this case, the last one that I have chosen is fourth degree. So it follows that you will have to determine 4 constants, 4 coefficients. So that really took time. Okay? Now, I'll go to our slide. So to recap everything that we have discussed, these are what you need to do. You set up the partial fraction decomposition with the unknown constants A, B, C, etc. in the numerator of your decomposition. So the decomposition is when you write the original rational expression into its equivalent partial fractions. So isa ka rational nga integral, equivalent yan na, depende. May 3, may 4, may 2. Then you have to multiply both sides of the resulting equation by the least common denominator that was explained. Then simplify the right side of the equation. Then write both sides in descending powers, equating coefficients of like powers of x and equating constant coefficients or constant terms. You may use Heaviside when you are dealing with linear factors only. Solve the resulting linear system for A, B, C, etc. and substitute the values of your A, B, C, and other constant into the equation in step 1 and write the partial fraction decomposition. Then now you are ready to evaluate each of your partial fraction decomposition separately. Once you know already A, B, C, D, and so on and so forth. Now, study tip. You will encounter some examples in which the denominator of the given rational expression is not already factored. If necessary, always begin by factoring the denominator, then apply the 6 steps that you have here. If the degree of the numerator is higher or equal to the degree of the denominator, don't factor yet. First, perform long division. Okay? Next, don't represent a repeated linear factor in this form. This is repeated, and what is done here is just simply repeating the last. So I have said it a while ago also when I was pointing out the solution. The proper way of doing this is the last partial fraction should have a repeated linear factor. So this should have been quantity x minus 3 raised to 2 or squared. Okay? Next, when the denominator of a rational expression contains a power of linear factor, set up the partial fraction decomposition with constant numerators. So you still have A, B, C. When the denominator of the rational expression contains a power of a prime quadratic factor, set up the partial fraction decomposition with linear numerators. This is the case of quadratic factor. Okay, quadratic factor, the numerator is, as I have said, first degree or linear in nature. Ax plus b, cx plus d. Okay? When a rational expression contains a power of a factor in the denominator, be sure to set up the partial fraction decomposition to allow for every natural number power of the factor less than or equal to that particular power. So you could see this is x minus 5, then you have x minus 5 quantity squared, you have here x, you have here x squared, and you have here x cubed. You have a case of two repeated linear factors. One linear factor is x minus 5. The other linear factor is x. So it has been repeated here 3 times. This one was repeated twice. And so far, this is it for method of partial fractions. Do you have any questions? 1 minute to go and it's time for us. Any question? I will record. I will have this anyway. It's recorded now, so I will have this posted once I am ready with the link already available in YouTube. You can listen to this again. So on Wednesday class, you will have the quiz on what I just discussed. Okay, this one. And I may pick one here, okay, because the process here is very long. I will pick a number here that could be answered probably in just around 10 minutes. Then I will get some items in the hyperbolic. If you recall the last 2 slides which I recorded, the hyperbolic and inverse hyperbolic and the substitution. Probably I will get 2 from each topic and 1 here. So you will have around 5. Anyway, I'm solving them prior to giving it to you so I would know how long it would take you to finish your quiz. If you recall, I did not give any quiz on integration by parts because our discussion there was so limited. I promise you I will give you another slide, a recording of several shortcut manner of doing the by parts which you can listen to before your exam next week. But nonetheless, of course, you still have to study integration by parts because it will be given in your midterm exam. Okay? Any questions? I'm using up 1 minute of your time. Okay, so I will stop sharing now.